In this video, we're going to discuss the concept of enthalpy. So first, let's start with a definition of enthalpy. The enthalpy, which is abbreviated with the letter H, is defined as the sum of a system's internal energy and the mathematical product of its pressure and volume. Now I know that's a pretty confusing definition perhaps, but we will explain that and define it a little bit more as we move along. Now enthalpy cannot be directly measured experimentally. However, we are able to measure the change in enthalpy. So generally in chemistry, we're going to be talking about the change in enthalpy for a chemical reaction or a system, as opposed to just the overall enthalpy. The change of enthalpy could also be defined as the heat released or absorbed from a chemical reaction or physical process that's carried out at constant pressure. So again, what we want to do here in this video is take a little closer look at these definitions and try to make some sense of them, because enthalpy is a very, very important term in chemistry and thermodynamics. So first, let's start with a little bit of a discussion about molecules and internal energy. Molecules and atoms have internal energy stored inside of them. There's energy in there, and that energy can be in the form of kinetic energy. The chemical bonds in the molecule can be vibrating. There's rotational energy as the molecules move around. There's also potential energy that is stored in the chemical bonds. So the chemical bonds are holding the atoms together, and so therefore they can contain potential energy. So as an example, one we're fairly familiar with, let's look at octane, which is the major ingredient in gasoline. So this is the chemical formula for octane. And octane has energy stored in it. Now, when we take that gasoline or that octane and we react it or combust it, we release energy, right? So we can take gasoline, and we know if we light it on fire or combust it in the presence of oxygen, that it releases a lot of energy. There can be an explosion, fire, all this. So that energy comes from the energy that is stored inside of the molecules of octane. Now that's just one example. There are lots of other examples. ATP inside your body stores energy, propane, lots of other high energy molecules. So what happens to the internal energy when we take octane or gasoline and we combust it? So here we have the chemical formula, the chemical equation for the combustion of octane. So we're essentially just reacting octane with oxygen, and we're getting carbon dioxide, water, but we're also releasing or producing energy. So what can we say about that internal energy of octane? Well, a system can exchange energy with its surroundings either by transferring heat or by doing work. So when we take octane or gasoline and we combust it, that energy that's released is either going to be released as heat, or that energy can be used to do work. Now that's very important. Taking chemical energy that's released, and using it to do work. Now we can see this in our cars. When we combust gasoline in the engine, that energy is used to do work, make our car go. It moves piston up and down, ultimately makes the car move. We also have reactions that take place inside of our body, and the reactions release energy, and that energy can be used to do work, move our muscles, cause our heart to beat, all of these things. So chemical energy can be released as heat, or I should say the internal energy that's released from a chemical reaction or physical process can be released as heat or can be used to do work. So very important concept there. We can write this mathematically, as you see here, where delta U is the change in internal energy. So this is the energy that's going to be released when we combust our octane or some other reaction. And that energy that's released is equal to Q plus W, where Q is the heat that's going to be released or absorbed. Reactions can, of course, absorb those. And W is the work. So let's talk a little bit about the heat and work a little bit. Before we move into enthalpy, let's just be sure we're clear on heat and work because these are very important concepts. So the change in internal energy, the energy that's released or absorbed from a chemical reaction, can be released as heat or absorbed as heat. So let's talk about Q first. So here we have a picture of a chemical reaction that's occurring in a container. This container has a piston on top, which can move up and down. And if this reaction releases heat, then heat is going to be flowing out of the system into the surroundings, right? So we assign that value of Q, we give it a negative value. The negative sign simply indicates the direction of heat transfer. So if heat is transferred from the system to the surroundings, it is considered exothermic and the sign of Q is always negative. Conversely, if we have a reaction inside a container and that reaction absorbs heat, so heat is transferred from the surroundings into the system, in this case, we assign that Q value, the heat, a positive value. That simply means that the heat is being transferred or absorbed by the system. And we call these reactions endothermic. Okay, so that's just a little bit about the heat. What about work? Let's talk a little bit about work. Work is defined as a force acting over a distance. So if I were to apply a force over some distance, for example, if I pushed a chair across the room, I'm applying that force over some distance, right? I'm applying a force to the chair, pushing it across some distance across a room. So that is how we can define work. Now in chemistry, we often talk about work as pressure volume work. So that means when we have some volume change, let's say we had a reaction that occurred in a container, and when that reaction occurred, it caused that container to expand, right? The volume increased, or the volume could decrease. But if we expand the volume, then we're applying a force outwards, causing a change in volume. Now, if the volume is changing, the pressure often remains constant. Okay? So when we talk about work in chemistry, we often define it as pressure volume work, also can be called expansion or contraction work. And the formula for work that we often use in chemistry is work is equal to negative P, where P is the pressure, and delta V, the change in volume, right? So we said that when we have work, pressure volume work, we're changing the volume, but we're keeping the pressure constant. Now the negative sign, that is going to indicate the direction of work, and we'll define that here in just a second. But this is a formula that we often use in chemistry when we're defining work. So let's define that a little bit more. Let's say again, here we have a container that has a piston. This piston can move up or down. Let's say we have some chemical reaction in here and we ignite it. Maybe it's octane and we combust it. We produce a lot of gas, and that gas pushes outwards, causing the volume to increase, right? So here, work is being done by the system on the surroundings. The work is pushing upwards or outwards, causing the volume to increase. So if work is being done by the system on the surroundings, then work is essentially flowing out. So we want to give the work a negative sign. Again, the negative W, if we have a negative here, that just indicates that work is flowing outwards. Kind of like heat is flowing outwards, we give Q a negative value. So if the volume is expanding or increasing, then work is being done by the system on the surroundings. A positive delta V, right? Our delta V is increasing, so it's increasing, and we'd have a positive delta V. So that's why we have that negative sign there. So if delta V is positive, that's going to give us a negative W, indicating that the work is essentially flowing outwards. Think of it like heat. Now, conversely, if we have a reaction that takes place in here, and maybe we reduce the number of gas molecules, in this case, the volume would decrease. in this case, work would be being done by the surroundings on the system. In other words, the surroundings are pushing against this, pushing it down, decreasing the volume. So here, our delta V is going to be negative, but work is essentially flowing in, not out. And so in that case, we want W to have a positive value. So to kind of counteract that negative delta V, we have to have that negative sign, which would give us a positive work value here. So the positives and negatives, of course, in work or heat, they just indicate the direction of which the work is being done or the direction which the heat is flowing. So again, when work is being done by the surroundings on the system, we need a positive W, positive work. Now, in regards to this, it's about work, it's very important to note that work can only be done on a system under conditions of constant pressure. Now, when we talk about constant pressure, we're also saying that that's another way of saying that we're changing the volume. If the pressure is constant, then the volume is changing. So under conditions of constant pressure, our volume can expand or contract in order to maintain constant pressure. Now, this is very important because most all of the real world reactions that occur under constant pressure conditions. All of the reactions that occur in your body, in living things, these are essentially under constant pressure. They're not in sealed containers. Reactions that occur in a laboratory are generally constant pressure reactions. Anything that's open to the air in a beaker, constant pressure. So most all the reactions that are generally performed are under constant pressure. We can perform reactions under constant volume. In this case, we would have a change in pressure, but our volume would remain constant. But if we keep the volume constant, that's essentially like saying we're performing a reaction in a bomb calorimeter, in a sealed container that cannot expand or contract. So if there's no expansion or contraction, no work can be done. So work can only be done under conditions of constant pressure. So if we want to use chemical energy to do some kind of work, like in your body, in a car, some machine, we carry that out under conditions of constant pressure. Now, let's take a look at that, just maybe kind of show it mathematically a little bit. We've already said that if a reaction has a change in internal energy, that internal energy can be released as heat or it can be used to do work, right? So let's look at that under constant volume. Let's say we have the heat is being released. Our system is under constant volume, right? So Q sub V is our heat transferred at constant volume, and W is the work. Well, at constant volume, see, we just rearranged this. We've moved our Q out there and solved for Q of sub V. So our heat released at constant volume is equal to the change in internal energy plus the pressure change in volume. So we've just rearranged this equation. And since we said under constant volume, no work can be done because the change in volume is going to be equal to 0, right? So that term would be 0. Then under constant volume, all of the internal heat, all of the internal energy that's released must be released as heat. What about under constant pressure conditions? Well, here we have Q sub P is our heat released at constant pressure. W is our work. So let's solve for Q sub P. And if we rearrange that algebraically, we get this. Q sub P is equal to the change in internal energy plus our pressure times change in volume, because we can do work. This value is generally not equal to 0. So you can see how mathematically under constant pressure, constant volume, we essentially have two different equations because the internal energy can be released as heat or can be used to do work. So we haven't discussed enthalpy, so let's bring in enthalpy here. This is the equation that we were just looking at. If we are carrying out a reaction under constant pressure conditions, then the heat that's released is equal to the change in internal energy plus our pressure times change in volume, so the work that's done, right? Remember our definition of enthalpy from the beginning. The change in enthalpy, or enthalpy, can be defined as the sum of a system's internal energy change and its mathematical product of its pressure and work change. So this equation here is equal to the enthalpy change. So our enthalpy change and our heat at constant pressure are essentially the same thing. So let's show that one other way. So we've shown you here that we can just replace Q sub P with delta H, and we get this equation. Now remember, our change in internal energy, we said that change in internal energy, that energy can be released as heat or can be used to do work. So if we take this and we replace it or put it in for our change in internal energy, then we essentially get this equation here, where Q sub P minus P delta V plus P delta V. Notice that these cancel, and that tells us that the change in enthalpy is equal to the heat released from a chemical reaction, the heat released or absorbed, when that reaction occurs at constant pressure. So delta H, our enthalpy, this is a much more practical definition, one that we often use more often in chemistry. Our enthalpy change is equal to the heat released or absorbed from a chemical reaction or physical process that's carried out at constant pressure. So back to our talk about gasoline. If I were to combust gasoline or octane, it releases a lot of heat, right? If that reaction is carried out under constant pressure, then the heat that's released, we can just call that the enthalpy change. They're the same thing. Now that's important because enthalpy changes, just like heat that's released or absorbed, we can measure that experimentally using calorimetry, right? So we can't measure enthalpy, but we can measure enthalpy changes, because the enthalpy change, as we said, is equal to the heat that's released or absorbed when the reaction is carried out under constant pressure. Reactions or physical processes that release heat, we give those a negative delta H value, just like negative Q. And we say these are exothermic processes. And reactions or physical processes that absorb heat, we give those a positive delta H, positive enthalpy change, and we call those endothermic. So one final thing about enthalpy is that generally when we're measuring enthalpy or comparing enthalpy between reactions, we like to be sure they're carried out under or measured under the same conditions. So a lot of reactions are often carried out under what are called standard state conditions. So you may see a standard enthalpy of a reaction that's measured, and the standard enthalpy is designated by the little degree sign. That means that the enthalpy change that's being measured was carried out under standard thermodynamic conditions. Those conditions include that we have a pure substance in its most stable form. The reaction takes place under 1 atmosphere of pressure. The temperature is 25 Celsius. And if we're talking about solutions, all of the solutions are at 1 molar concentration. So if you ever see standard enthalpy, it just is the enthalpy change for a reaction that was measured under these standard state conditions. So enthalpy is a very, very important thermodynamic term. Be sure you understand what it means and basically how it's derived.